Hello everybody. In this video we are going to start talking about the use of the information that we have been discussing in the previous videos about the heat of reaction in the energy balance equation. And this is something that we have been discussing for many videos before. That we were talking about the calculation of delta H. This is the term that is a term that we cannot measure, and we did a lot of things in order to calculate delta H. In chapter 7 we did this using the steam tables. In chapter 8 we started to find out what are the sources of enthalpy change, either the change in temperature, either the change in pressure, either the change in phase, or mixing. We didn't cover mixing, but mixing is one other reason. And here in this chapter we want to see, if we have a chemical reaction, how can we calculate the change in enthalpy due to the reaction. And this is a very important thing. And in this video I will make this as an introduction to the methods that we use to do the calculations. So the calculations are going to be easy. They are long, but they're easy. There is no complicated thing about the calculations. It takes time, as we saw in chapter 8. It's going to be similar to this, but from the conceptual point of view, it's not complicated. But what I want to do in this video is an introduction, and I'm making this introduction, which is not in the textbook, but I'm making this introduction because, based on my experience with the students, there are some points that are not very clear, and they have to be clarified before we proceed, to make it easy for you to understand what is going next, or why we do the calculations that we will do later. So what we will do is we will take an example, and we will keep moving on with making it more complicated by making more constraints on the example, until we reach a point where we will ask a question which we will answer in the coming videos, inshallah. So this is just an overview of what we are going to do today, just to make you aware of what is the goal of this video. So for the example that we will cover here, we have ethane that is thermally cracked to produce ethylene and hydrogen. So it's just a reaction to break the ethane into ethylene. And the example that we have here says that the temperature of the feed and the product streams, as we see here, are 25 degrees Celsius. Both temperatures are 25 degrees Celsius at the standard temperature. We have 100 moles per second of ethane in the feed, and the conversion is 100%, which means that 100 moles is going into the reaction. They are totally consumed, producing 100 moles of ethylene, and 100 moles of hydrogen, which we have here. So this is what we have, and we want to calculate the amount of heat that must be supplied to the reactor in order to achieve this reaction or this conversion. And in order to do this, we will start with the same equation that we have, which is the energy balance equation. In this equation we have in this system we have no work. It's just a reactor. There are no pumps, no compressors, no moving parts, no shaft, and we will ignore the changes in the kinetic and potential energies, and so the equation would be simplified to be, or will reduce to, Q equals delta H. So if I want to find the amount of heat to be supplied to the reactor, we need to find the difference in enthalpies. The difference in enthalpy is the enthalpy of the product stream minus the enthalpy of the feed stream. So this is what we want to do. If you look at these two streams, you would see that they are both at the same temperature, so there is no temperature difference. There is we will assume that the pressure is the same, so there is no change in pressure. Both phases are gas phases, which is not something that we can mention here, because we have different materials, we have different species, ethane at one side, ethylene and hydrogen on the other side, but anyways they are gas. So the only cause, and this is the point that I want to stress on, that the only reason for the change in enthalpy is the reaction. And I want to go back to the list of the causes of or the cases of calculating the change in enthalpy and change in internal energy, one of them was the chemical reaction. So the chemical reaction by itself, is one reason for changing the enthalpy of the in the system. So if you want to know how much heat or how much enthalpy is change is, we can calculate it using the equation that we derived before, that the change in enthalpy due to a chemical reaction is the extent of reaction multiplied by the heat of reaction. The heat of reaction here is going to be at standard conditions, so we can calculate it using or we can calculate the standard heat of reaction from the heats of formation. So it's the heat of formation of the product, which is ethylene and oxygen and hydrogen, because hydrogen has zero heat of formation, minus the heat of formation of the reactant, which is ethane, and this will give us the total enthalpy change. So Q is going to be positive. Of course, this is expected. We are saying that this is thermal cracking. So thermal cracking is a reaction that requires heat. So this will have a positive Q, which is heat supplied to the system. So this is a very good example to start with, and there are some points that I want to comment on about this example. The first is that the way we calculated the change in enthalpy is not the same way that we used to do in non-reactive systems. In non-reactive systems, we used to use the equation of delta H equals N multiplied by delta H. And if we have a mixture, we assume it's an ideal mixture, so it's the number of moles of each one of the components multiplied by the change of enthalpy of this component. The same for the second with the delta H of the second, and the same for all of them. In our case, we cannot apply this equation because we have no C2H6 in the feed, in the product, and we have no ethylene or hydrogen in the feed. So when I say delta H of ethane, it's ethane in the product, which is not there, minus that in the feed. And for C2H4, it's the enthalpy of C2H4 in the product minus that of the feed, which is not there. So I cannot apply this equation anymore because this is a reactive system. This is a reactive system. So I cannot apply this equation to a reactive system. So this equation must be very clear. We cannot deal with a reactive system with the same way we deal with non-reactive systems. Exactly the same thing we did with mass balance. In mass balance, when we dealt with non-reactive systems, we will just say N equals out. This is all what we said. In non-reactive system, in reactive systems, we had to either do the atomic balance on the reactor, or to do the calculations of the extent of reaction to calculate the number of moles of the product, or to do the mass balance on the mole balance on the reactor. So this is the same thing. The equations that we use for non-reactive systems are different from the equations that we use for reactive systems. Or the equations contain terms that are different. So this is the same thing here. We cannot use this equation anymore for the reactive systems. So now comes the question: what is the equation that we use? The term that takes care of this is the heat of reaction. And I want to go back to the definition that we started with in this chapter about the heat of reaction. We said that the heat of reaction is the enthalpy difference, which is delta H, the enthalpy difference when stoichiometric quantities of the reactants at specific temperature and pressure react completely, and the products are at the same temperature and pressure. If you go back to this case here, this is exactly what we have. We have the reactants. Of course, it's one reactant, so there is no stoichiometric ratios. But this is the reactant at 25. The product is at 25. It's totally consumed. So this is the definition of the heat of reaction. So the heat of reaction is enthalpy difference. It's an enthalpy difference. This is by definition. The heat of reaction is an enthalpy difference. So when we have a reaction, the way we account for the change in enthalpy is using the term of heat of reaction. So I'm stressing on this point because I got from my experience with the students, it seems it's not very easy to grasp and to understand. So I'm trying to stress as much as I can to make sure that this point is clear. So in the previous example, we had the feed and the product are both at the standard temperature, so we were able to calculate the enthalpy change as the extent of reaction multiplied by delta H R naught. And we did the derivation for this term before, and we said that delta H R naught is the enthalpy change for 1 mole of ethane being broken into ethylene and hydrogen, or cracked into ethylene and hydrogen. So if you want to account for all the ethylene that is cracked, we will multiply it by the extent of reaction. The last point here is that the example that we solved was based on some assumptions which are not valid for most of the cases. For example, we said that the conversion of ethane is 100%, which doesn't happen in I would say 95% of the reactions. So we don't get this 100% conversion. The second is that we assume the feed and the product are at the same temperature, which is also not a realistic assumption, because in most of the cases the reactions happen at different temperatures. So what we will do in the coming slides is we will try to take this example to be more realistic. So we will take it one by one. So for this example here, it's the same example with one difference, that the conversion of ethane is 70%. So we have here 100 moles of ethane. 70% are converted, so we have 70 moles of ethylene and 70 moles of hydrogen, and only 30% are ethane, which are 30 moles, which are not converted, which come out as a product. So if we want to calculate the enthalpy difference here, we will do the same thing. The energy balance equation will be simplified to BQ equals delta H, and now this schematic diagram is going to be very helpful. So here we have ethane. Okay, we have 100 moles. 70 moles are converted into ethylene and hydrogen, and only 30 moles are coming out as ethane. So this 30 moles started or were fed to the reactor as ethane gas at 25 Celsius and come out as ethane gas at 25 Celsius. So the enthalpy difference for this part is 0. It's just ethane that went into the reactor, didn't react, and came out of the reactor as it is, with no change in temperature, with no change in pressure, with no change in phase. So there is no enthalpy change. So when we calculate the change in enthalpy, it's going to be only for the 70 moles that reacted. So the reaction, or the change in enthalpy, is only due to the reaction of 70 moles per second of ethane. So we can write the equation as delta H equals the extent of reaction multiplied by delta H. The extent of reaction here is going to be 70. It's going to be out minus n over the stoichiometric coefficient. So it's going to be 30 minus 100 over negative 1, or 70 minus 0 over 1. So it's going to be 70 at the end of the day, multiplied by the same standard heat of reaction to be whatever the value that we have. It's 9.6 times 10 power 3 kilowatts. So this is what we will do if we have conversion that's less than 100%, but still we have an assumption that the reaction takes place at the standard conditions. So now we want to make it more realistic by changing the temperature. So you'll have the feed at 500 degrees Celsius and the product at 200 degrees Celsius. And now we will have the same energy balance equation that reduces 2Q equals delta H. And now there is something different. So if you look at the conditions that we have here, you would see here that we have ethane at 500 degrees Celsius, 70 moles of which are converted into ethylene and hydrogen at 200 degrees Celsius, and 30 moles are converted into or come out as ethane, but at different temperature. So here we have delta H, and here we have delta H. So when we have different temperatures, the enthalpy changes due to the reaction, and there is also change in temperature that must be taken into account. And the reaction itself is not at the standard condition, so I cannot use the delta HR node as I used to use before. So now we have a question that we want to answer is, how can we calculate delta H considering both causes of enthalpy change, which is the change in temperature and the change in and the chemical reaction. And this is the point I want to make from this video, that we understand now where we are standing and the problem that we are facing, or the challenge that we are facing, and we want to find out how to manage or get this delta H calculated. The way we are going to do this using one of two methods. One of them is called the heat of reaction method. The second is called the heat of formation method. We will go through the two methods in the coming videos, inshallah, in details, and we will understand how or what is the philosophy of each one of them, and how we can convert this philosophy or this idea into equations. This is going to be what we will end this course with, just to understand these two methods and apply this on some examples, and that's it. But the point that I want to make sure that it's clear that we have a challenge here that is making us go through these two methods. That we have a reaction that causes change in enthalpy, and that the reaction happens with conversion in less than 100%, and that we have components that are converted into other components, and that the temperatures are different from the temperatures of the standard conditions. The temperature of the feed is different from the temperature of the product. All of this must be taken into consideration, and that's why we will go through these two methods. So I hope this point is clear, and we will continue inshallah next time with the first method of the two. So I'll see you then inshallah. Goodbye.